Alright, last section in chapter 3, 3.6, prove theorems about perpendicular lines. The distance from a point to a line. The distance from a point to a line is the length of the perpendicular segment from the point to the line. So, for example, if you had a line like this, and some point not on the line, the distance from that point would be this segment here, the segment that is exactly perpendicular to the line. Okay, Theorem 3.8. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. And this actually makes sense if you think about it. A linear pair, as you guys know, they're always going to be supplementary, which means they add up to 180. So if these two angles have to add up to 180, and they're congruent, well, then they both have to be 90 degrees, right? Yeah, because that's the only way they can be the same measure and both add up to 180. So if angle 1 is congruent to angle 2, then G is perpendicular to H. Theorem 3.9, if two lines are perpendicular, then they intersect to form 4 right angles. Okay, so if these two lines are perpendicular, they don't just form one right angle. All 4 of these angles are going to be congruent. Okay, so angles 1, 2, 3, and 4 are all right angles. Okay, for example, example 1. In the diagram at the right, angle 1 is congruent to angle 2. What can you conclude about A and B? Lines A and B intersect to form a linear pair of congruent angles. Angle 1 and angle 2. So by Theorem 3.8, A is perpendicular to B. Now, in your proofs, I've mentioned this before in class, but in your proofs you don't have to write down the number of the theorem. You could just write down what the theorem says. I'll be honest, I don't even remember all the numbers of the theorems, and if you use a different textbook, the theorems are going to have different numbers. So don't worry if you don't memorize the exact number of the theorem. Alright, let's go on to page 2. Excuse me. Theorem 3.10. If two sides of two adjacent acute angles are perpendicular, then the angles are complementary. Remember, complementary means they add up to 90 degrees. Now this makes sense because if these two lines are perpendicular, then they're going to form a right angle, a 90-degree angle. So of course, these two angles have to add up to 90 degrees because they are the two angles that make up the 90-degree angle. So if ray BA and is perpendicular to ray BC, then angle 1 and angle 2 are complementary. Alright, in the diagram at the right, I apologize that it got cut off. Let's see here. This is an S. This is an R. This is a 4, and I think you can see everything else okay. There are arrows at the end of the lines, of course. Given, angle 1 is congruent to angle 2. That's given. Because they're congruent, and as you can see, they're a linear pair, we know that PS, and there's actually, PS is right there. I think you can see that, but if not, there you go. PS is perpendicular to PQ. You could also call this VQ, because there's a V down here. Either way, it's fine. Theorem 3.8, or you can write down linear pair of congruent angles. Which is basically what that theorem says. That's fine too. Angles 3 and 4 are complementary. You could write Theorem 3.10, or you could write down, you could just write down that PS is perpendicular to PQ, which is essentially what that theorem says. It says that if these two lines are perpendicular, then obviously these two have to be complementary. Okay, so either way you want to do this. Alright, You guys go ahead and do this checkpoint. Let's go on to page 3. Okay, Theorem 3.11. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. Okay, so if H and K are parallel and J is perpendicular to H, then J is also perpendicular to K. Which makes sense because this angle and this angle are corresponding angles. And we already know that corresponding angles have to be congruent if the lines are parallel. So if this makes a 90-degree angle, this also has to be a 90-degree angle. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this is says kind of the same thing as what this one says, except in reverse. Over here I said that, over here the theorem said that if the lines are parallel, then these two both have to be right angles. Here it says if these two are both right angles, then these lines have to be parallel. So if M is perpendicular to P and N is perpendicular to P, then M is parallel to N. Okay, determine which lines, if any, must be parallel in the diagram. Explain your reasoning. Okay, lines R and S are both perpendicular to X. As you can see here, R is perpendicular to X and S is perpendicular to X. So by Theorem 3.12, R is parallel to S. Similarly, lines X and Y are both perpendicular to R. As you can see, X and Y, X is perpendicular to R, Y is perpendicular to R. Excuse me. So X is parallel to Y. Also, lines X and Z are both perpendicular to S. Okay, so X is perpendicular to Z. Finally, because Y and Z are both parallel to X, you know that Y is parallel to Z by the transit property. Basically, if X is parallel to Z and X is parallel to Y, then Y and Z have to be parallel also because of the transitive property. Okay? Alright, I'll let you guys do these two. Let's go on to page 4. Okay, railroads. The section of broad gauge railroad track at the right are drawn on a graph where units are measured in inches. And gosh, it got cut off again. What is the width of the track? Okay, I'm going to try to draw what's missing here. This says Q 7134. And this is P 9155. Okay? So, you need to find the length of one of the perpendicular segments. Okay? Or of a perpendicular segment, singular. There we go. From one side of the track to the other. Using Q7134 and R9155, the slope of each rail is 55 minus 34, 91 minus 71. 55 minus 34 is 21. 91 minus 71 is 20. So that's the slope of each rail. The segment PQ, it's this one here, has a slope of 74 here. I'm using these two and these two. I'll write them down over here. Okay, so 74 minus 34 and 29 minus 71. 74 minus 34 is 40. 29 minus 71, that's, let's see here, 42. So this is negative 20 over 21. Hopefully you guys can see these two are opposite reciprocals of each other. Basically, if I were to flip this over and change the sign, I would get this one. And if I were to flip this one over and change the sign, I would get this one. Because they're opposite reciprocals of each other, I know that these two lines are perpendicular. Okay? The segment PQ is perpendicular to the rail. So, let's see here. PQ, I'm going to look for the, I'm going to use the distance formula to find the length of it. These are the values I'm going to use. Here's x1, y1, x2, y2, and I'm actually going to write the distance formula over here just in case you guys don't remember it. D equals x2 minus x1 squared plus y2 minus y1 squared. Okay, so in this case, x2 is 71, x1 is 29, y2 is 34, y1 is 74. 71 minus 29, 42. 34 minus 74, that's going to be 40. So I've got 42 squared plus 40 squared. Now I'm going to pull out my calculator for this one. Alright, 42 times 42. D equals, oops, missed it. Alright, there we go. 1764. 40 squared is going to be 1600. Let's pull out the calculator again. 1764 plus 1600. 3364, square root of which is 58. So, the width of the track is, here we go, 58 inches. Okay? Alright, I'll let you guys do the last checkpoint. It got cut off here, but it should be fine in your notes. Okay? And that's all for today.